Well, good morning, good afternoon, wherever you are in the world. We'll get started in 30 seconds to a minute. I see we have 33 attendees. We might be expecting a few more, so we'll get started pretty much on time. All right, my little start timer has expired, but let's give it just another 30 seconds to make sure that we have most of the folks who are attending on the call. Okay. Well, hello everyone, and welcome to the Design Expert New User Webinar. The goal of this session is to help new users become familiar with design of experiment concepts and to introduce Stati's Design Expert software for the creation and analysis of multiple types of experiments. By way of personal introduction, my name is Richard Williams, and I've been a Stati's consultant for a few years now. Prior to that, I spent 38 years in the chemical industry in roles focused on product and process development and improvement. By training, I'm a chemical engineer with a business degree, and I'm also a Six Sigma Master Black Belt. In my experience, I feel DOE has been underutilized for problem solving and process optimization, but I also think DOE should be the tool of choice to help us launch reliable products and processes from the very start. That's the idea that is behind quality by design, or design for Six Sigma. Over the past 10 years or so, I focused on providing training for product and process improvement tools. So today I'm happy to provide this webinar to get you started with design of experiments. Now, I will say this is a big topic, and we're only going to be able to scratch the surface in 1 hour. But I will give you, I will certainly give you your money's worth for a 1 hour webinar. You're going to see a lot of different tools and topics. And we're going to offer you resources along the way so that you can do a little bit deeper dive when you find things that you feel you could use more completely. Okay, so we're going to throw a lot at you. Grab what you can. We're also, well, let's get to the next slide. We are also going to, making the most of this learning opportunity. So to prevent audio disruptions, everyone is on mute on the call. Hopefully not me. I think I'm coming through okay. During the webinar, though, questions will be monitored in the GoToWebinar Questions tab or the pane. So if you look at your GoToWebinar controls, Sherry Kraber is on the call, and she will be answering questions that you may have directly in the GoToWebinar pane. Okay, we'll get to as many of those as we possibly can. If your question is a little bit more lengthy, more than just a clarifying question, she may need to follow up with that. And if you have questions after the webinar, please send those to stathelp@statis.com. And if you're using the software, please provide your company name and the serial number of your software license if you can. The slides and a recording of this webinar will be posted on the Statis webinars page within a few business days, right? So even though we're going quickly today, you'll have an opportunity to kind of revisit this material in the coming days. Okay. So the goals, I'd like us to think about why we would want to consider DOE type methods as opposed to other alternative experimental approaches. I will introduce Design Expert by demonstration. We'll actually go through 3 example problems today, so I got to stick right with the plan here. And we'll give you an awareness of applications for DOE and types of designs. So just to make sure that we're all here and awake and alive and the voice is coming through before I get too far, if you could go into your GoToWebinar controls in the attendee section and give me the raise your hand flag just to let me know I'm coming through and things are okay. There are some. Excellent. Okay. All right. Thank you. So let's get going. So the agenda, I will talk about DOE in general and, cover what's in it for me. Why would you think about doing this anyway? Then we'll get into three specific design types. One will be called a factorial design, and we'll learn what those are about. We will also get into a response surface, and then also a mixture design. Formulations have some special characteristics to them, and we will use a little bit special tools in order to handle a mixture design. Okay, so that's where we're headed. So what's in it for me? Why do we want to do this? Well, when we view most things that we cover in DOEs, we typically think of a process, right? So let's just take one we can all relate to, maybe making cookies in a kitchen. Okay, that's my process, right? I make my batter, I put cookies on a cookie sheet, and I put them in an oven for a certain time and temperature, and then I measure something. I measure perhaps the flavor, right? I might have 5 different tasters who we might average their scores as a response, right? So our goal in DOE is to evaluate the controllable factors, maybe the time and the temperature in the oven or the oven rack, a categoric choice of rack A, B, or C. I can look at these controllable factors and I can look at the impact that they might have on a response. Perhaps the flavor of a cookie, the rating of the flavor, or the percentage of the cookies that are burned, or something like that, right? So the yield. But the problem that we have in the real world is we want to establish these relationships between X's and Y's in the presence of noise factors. Okay, we always have noise. Every process contributes noise factors. In this little example of mine, perhaps the flavor rating, my test panel might rate the flavor of a cookie differently on different days. So there might be some measurement system error introduced, some noise from the measurement system. When I try to bake my cookies for 13 minutes, I might take them out at 12 and a half or 13 and a half, so that my control of my factors might wander around a little bit, and that would have an impact on my response. So we always have noise in the system, and the goal of any experimental approach, including DOE, is to establish the X and Y relationship, despite the fact that we have these noise factors trying to corrupt the analysis, trying to disguise the relationship, right? So that's kind of the goal. And the statistics in DOE will help us establish those relationships with confidence. We will also do multi-factor testing rather than one factor at a time. Now, we may have been taught or led to believe that the best way to do an experiment is to keep everything constant and change one thing at a time, one factor at a time, because the logic goes, if you move more than one thing at the same time, you can't possibly make sense of the story, right? Well, that's where the mathematicians come in, and we begin to learn that actually, if we do change more than one thing at a time in a very carefully orchestrated way, we can definitely understand the impact of the factors, but more importantly, we can identify interactions. Okay, so what's an interaction? Well, first of all, one factor at a time experimentation cannot identify this thing called interactions, and interactions frequently play a key role in process improvement. Okay, so let's just think about this for a minute. The time and temperature impacting the yield of cookies, right? Too much of both might burn the cookies, but not enough might leave them unbaked. So on the graph in the upper right, this is an interaction plot, and what we see is temperature along the bottom, low and high, and we have yield along the edge, and we want to figure out the relationship between temperature and yield. However, we have another factor. We have the time that we leave it in the oven, and what we see if we use the dotted line, the short amount of time, is that our yield is low at low temperatures because we're undercooking the cookies, right? So we don't have a good yield. We haven't sufficiently cooked them. And as we increase the temperature at the short bake time, we improve our yield because more of the cookies are fully cooked. On the other hand, if we go with the solid line on this graph, we have, that's going to be a long cooking time. And at low temperature, we do okay, we have a high yield, but suddenly if we increase the temperature and cook them at a long time, our yield drops off. Why? Because we're burning some of the cookies. So if you look at that graph, you can see that the impact of one factor depends on the set point of the other factor. It depends on the level chosen for the other factor, right? So one factor at a time experimentation cannot identify those interaction relationships. You need to go into a DOE type situation in order to establish those. So DOE multi-factor experimentation, by its parallel processing, provides more information. You can find these interaction terms, okay, and that's a key thing. Moreover, the statistics within the DOE provide confidence in the finding, right? It's so often we find relationships, or we do insufficient data, collect insufficient data, and we think we found relationships when in fact all we're finding is random noise in our experimentation. So we want to be able to establish the X and Y relationships in the presence of noise and have confidence in our findings. Now within Design Expert, we have several different types of analyses that we can do. We often refer to the SCO strategy, the screening, characterization, and optimization. So a screening design is a design where maybe we have several different factors that we believe might be impacting our process, and what we want to do is discover which ones actually have an impact and which ones are irrelevant. So a screening design is one that we can come in and with as little work as possible, establish which factors are dominating the process, which are really controlling the situation, okay? Characterizing now allows us to take the factors that survive the screening process, those that we know have an impact, and now what we can do is we can look for and quantify the impact of those critical factors, and also discover the interactions that are taking place amongst them. If we want to truly optimize a system, oftentimes we might want to come back in and do a response surface, and we'll get into that a little bit more completely as we do our examples. Okay. So we have a bit of a recipe that we will go through for design of experiments, and just kind of outlines what we want to do. First of all, we always want to define the objective in terms of measurable responses, right? I want to improve the flavor of my cookies. Okay, well, how do we decide what the flavor of a cookie is? Well, we have 5 taste testers and we average the score, whatever we decide, okay? But we want to define the objectives in terms of measurable responses. Then we want to select the input factors to study. Okay, now we might sit down together and think of 10 different things that could impact the flavor of a cookie. And we may settle on this study, leaving the formulation untouched, and we may come back and say we want to look at time and temperature in the oven, and perhaps the oven rack that we use, okay, or the type of cookie sheet that we use. So those could be things that we would look at. And then what we're going to do in step 3 is select your design. That's going to be where our software will help you choose the type of experiment that you should conduct, the layout of the factor levels, and a run-by-run sequence. Then you get to do the hardest part, and that's to conduct the actual experiment itself. And once you do that and you input the data, the software will then help you analyze the results using the statistical tools and graphical techniques. We will, in point 6, we're going to go through and take a look at any abnormalities in the data, potential outliers. So we have some diagnostic plots to make sure that the study has some integrity. Then we're going to give you some output graphs so that we can visually see what we have going on. We're going to give you some optimization tools so you can find the optimal conditions. And then typically we're going to recommend that once you've made your discoveries that you go back out and confirm it using a confirmation run. Okay, so you've used the tool, you've discovered your optimal conditions, then perhaps go out and actually, prove it by running those conditions and see if your results look appropriate. And it's up to you to figure out how to celebrate once this is accomplished. Well, let's get into a factorial demo, and we're going to characterize the vital interactions. So a factorial experiment is one where we're going to look for the impact of various factors and their interactions on the output. Okay, so that's where we're going to go. So like I mentioned, I'm a chemical engineer, so some of my examples are going to be a little bit more related to that area. So hopefully we can all relate just the same. Here is a reactor case study, and the goal of this now is to find the conditions that maximize the yield of a chemical reaction. Okay, so I have 5 different factors that our process experts believe could have some bearing on the story: feed rate, catalyst, etc. That last one, the atmosphere, is a categoric choice. We're either going to run this in nitrogen or just an air environment, right, to see if that has an impact. Okay, so the goal is to maximize the yield. We are going to do this little thing. Now this is a deep dive on a topic that is actually quite relevant to make sure that we are collecting enough data to answer the question that we have. We don't want to undersize our experiments. We don't want to collect too little data in order to answer the question. Otherwise, we're going to be dissatisfied with the outcome of this. So I'm just going to give a very brief introduction to the topic of power. And this is going to be one that you may have a need to revisit after the webinar a little bit. But here's the key ingredients to this thing called the power calculation. First is this choice that we make about the signal. And the easiest way to look at that is any improvement less than this chosen signal will be unimportant to us. And this is just something that we have to set for ourselves. It's a business decision or experimenter's decision. If we're trying to improve the yield of this reaction, we may feel that if we have factors that contribute, say, 1 or 2 percentage points, that it's okay to us that we don't detect those, that we miss them, because really we're looking for a material change in the yield of this reaction. So I might set a delta Y of 3 percentage points or even 5 percentage points. The smaller I make that number, the more runs I'm going to have to do. So I want to be realistic with that, right? I wouldn't want to make it, 0.1 percentage point, because that would be so small that it wouldn't be meaningful. But on the other hand, 10 percentage points would be probably too big. I mean, I want to find things that might contribute to 3 percentage point change. Now, the noise in the system, the variability that we have in this testing and the sampling and in the reaction itself and controlling all the factors, if we went out and tried to do the same thing 10 or 15 times and we collected a response, we collected, the results, we might be able to calculate a standard deviation because we wouldn't get the same answer every time. And that's really what we're talking about. That's the noise or the random variation that we see in this process when we try to do the same thing multiple times. All right. So let's get into the software and see how we would do this. All right. So when we open up the software, this is the opening page for Design Expert. This is version 13, the newest version. And I'm going to click on New Design. And it's going to default to this rather standard red, yellow, green design choice called Regular 2-Level Factorial Designs. Well, if you look on the left-hand panel, you see that there is a menu of several different kinds of design choices. Okay, probably the most common choice, the most commonly run type of design experiment is in fact these 2-level factorial designs, but there are other options, and you're going to see a few of them as we continue today. But in this case, we have 5 factors. So along the top, we have the number of factors that are involved, and then we have the number of runs on the left-hand side that will be involved. This diagonal line of white boxes is what's called a full factorial. A full factorial is when we study every factor at its high and low level in combination with all the other factors at their high and low level. So everything is tested together at the high and low levels. So we're going to do a full factorial. So I'm going to go to the 5-factor box and I'm going to click the 32 run example, and that'll be a full factorial. Now notice that we do have red, yellow, and green, and just above this 32 run design, there is one in green with 16 runs. That may be a perfectly valid choice that we could take in order to conduct this experiment. Okay, the green ones would help us to characterize main effects and these interaction terms, 2-factor interaction terms. Yellow are good for screening designs, and the red we really should avoid at all costs. Okay, so that's a little bit of what this slide is telling us. So then we're going to hit next now that we've chosen our design, and it brings up the input screen. In here we would go ahead and put our factors in here. This type in feed rate. I think that was liters per minute, and the range on this is 10 to 15 we decided, and then we would go on to the next one, etc. So what I'm going to do is I'm going to actually open up a design where I've actually input this information. So let's go ahead and do that. So we have this design, and here we've typed in all the different factors and their ranges. Notice that that last one is a categoric. I can have a little drop-down menu here for that one. I can change it from numeric to categoric, and it's either nitrogen or air. So we can deal with those kinds of factors as well as numeric factors. I'll hit next. And this is where that's going to do this little thing called the power calculation. Remember that delta Y that I said that was going to be 3 percentage points. We want to find things that contribute at least a 3 percentage point change in yield. And we said that the noise, the standard deviation, if we try to do the same thing multiple times, that was 2. So the signal to noise ratio is 1.5, 3 divided by 2, okay? That's what drives this thing called power, the ability to find what we're looking for. So if I hit next, it'll do this little power calculation, and it says that if in fact factor A, for example, causes a 3 percentage point change in the yield, that I've got a 98% chance of discovering that given a noise or standard deviation in the system of 2. That's pretty good. We typically want to be at least 80%. 80 to 95 is pretty much typical. You can go a little higher, but we want to make sure that we have collected sufficient data, but we don't want to go crazy. We don't want to have, add the cost of doing extra work if we can avoid it. Then we will finish the design, and it goes ahead and creates our 32 run design, and it gives us these in random order. We want to run our experiments in random order, okay? Well, why is that? Well, let's think about this. Let me sort on this temperature, this last one. Right, so it says I'm going to do all of my low temperature runs, and then I'll come back and I'll do all my high temperature runs. Well, let's imagine that through the course of conducting these 32 experiments, let's imagine that there was something else taking place. Maybe the who knows what. Maybe the catalyst is losing its power. Maybe maybe I had to change raw materials halfway through the experiment. Well, now what's going to happen is if I have these lurking variables, it's going to confuse my those lurking variables that are changing through the course of time. It's going to confuse that with the impact in this case of factor C, this 4th factor, the temperature. So to avoid that, what we want to do is run these in random order so that everything is, well, it's random. And now if I have a lurking variable, then it's having an equal impact on all of the conditions. And even though it might introduce some noise in the system, I'm at least not confusing that extra variation with a factor that I'm trying to study. So randomization is important. Let's get my data. I have a quick way to do that. I'm going to use a little simulator. And this will call the Reactor. So it's a lot easier for me to get data than you, but there it is. We now have data. Once we have that, we have to go and do an analysis. So underneath analysis, I will click yield, my one and only response in this case. I will click start analysis. And that brings up two plots that will help me pick the terms of significance. I like to use this half normal plot on the left-hand side. And each of these little squares is a factor or an interaction term that could be involved. So let's just right click on one of these, and that one, that's atmosphere, right? We had a categorical choice of nitrogen versus air. So apparently that's a factor. Now what this red line represents, those factors that are no more powerful than random noise, okay? So anything along this red line, like this CD interaction, that's pretty much the same as random noise. So that is not statistically significant. For the further off this red line a factor is, the more significant it is. So the most important factor is going to be this catalyst, right? That's that little square way up on the upper right. So I'm going to select the ones that are important, everything that's not along that line. And those now are going to be brought into a mathematical model that will be used to make the predictions. Okay, so we're modeling our responses. Now what we have, so those are all selected, and on the right-hand side, we can double check on the Pareto chart to look for the terms of significance. And we have statistical limits there, the Bonferroni and the t-value limit. And what we see is the chosen factors are actually quite significant. So we're happy with that. Then we're going to jump to the ANOVA, the analysis of variance table. So what we're going to do is we're going to go along the top here, we're going to go left to right as we go through our analysis. Okay, so top to bottom on the left and left to right on the top is how the software is laid out. Now what we see is this model that we've chosen is significant. Well, how do we know that? Well, it says the model is significant in the ANOVA table. That helps. But what it's looking at are these p-values, and anything with a p-value of less than 0.05 is statistically significant with at least 95% confidence, right? So these are much lower than 0.05. So the overall model and each of the terms in the model are statistically significant. We also have some fit statistics that we look at in the upper right. We have, our square values, and in this course, in this webinar, we won't have time to delve into the meaning of all of those things, but we certainly understand that a higher R-squared number is in general a very favorable situation. We will also have on the bottom right the coefficients that belong in the factor, and then we have the predictive equation that's used in order to make predictions, right? So that's all in there. Once we're satisfied with the ANOVA itself, we can quickly look at some diagnostic plots, and that helps us to see if there's something funny going on with the data that we've collected. In this upper left-hand side, we want to make sure that the normal plot of residuals looks good. What does that mean? So the residual is our actual versus predicted for each of the data points, and we want those to be fairly consistent, and any variation that we see, we want that to be normally distributed. Well, in that graph, if it follows the red line, it is in fact normally distributed, and that looks fine. In the upper right, residuals versus predicted, well, we want to make sure that we don't have a megaphone shape on that chart. Okay, so in the full course, we get into the ins and outs of why we would want to do that. On the bottom left, we like to look at a plot called the Box-Cox to see if a data transformation would be helpful. Well, that's a deep topic, but the good news in this case is the recommended transform is none, so we know we're okay with what we have. And we'd like to look at the predicted versus actual to make sure that this line splits the data that we have, which it does, right? You want your predicted and your actual to be consistent throughout the range that you studied. So we're good. So we're satisfied with the analysis, and now we're going to get into the model graphs, okay? And in this case, we can pretty well find our optimal conditions just by looking at these graphs, all right? So in my model, I have, let's look at the ANOVA again briefly. In my model, I have B, D, and E, and then I have some two-factor interactions. And factor E is a categoric choice, the atmosphere, right? So I can sort of toggle that one back and forth. So if I look at what's going on with factors B and D, and I switch based on the atmosphere, nitrogen versus air, I should be able to see the story. So here in the model graphics, I'm going to plot B and D on this interaction plot. So B is along the bottom, and my two lines represent the two different temperatures, factor D. And over here on the left, you can see that the red line is the higher temperature at 180, and the black line is the lower temperature at 140. So yield is along the side, and we're after high yields, so we can see that in nitrogen, which is, if I look at this little toggle down here on the left, factor E is set at nitrogen. We can see what's happening. But let's take a look at this. Let's look at the categoric choice and make that go in air. Look at that. Everything drops down, and there's a clear interaction taking place as well. So we know that nitrogen is the better choice. So we'll click on that again. These little these little error bars are called least significant difference bars. Think of them more or less as 95% confidence intervals. But the idea here is these are all statistically significant and different from one another. And if I click on the one in the upper right, the best condition, it's comparing all the other ones now against the benchmark that I've chosen. So we see that all of these other conditions are statistically different than the one that I've chosen. And over on the left-hand side, it gives me a prediction. My yield for those conditions would be 93.6%. Okay. So without even having to delve into all kinds of complex math and just simply looking at the graphs, we've been able to optimize this system. Okay. So back to the slides. So factorial design summary, things to remember. Full factorial designs like this one test all possible factor combinations. You characterize and develop an understanding of all of the main effects and the interaction terms. Two-factor interactions, and in this case, all the way up to a five-factor interaction, which would actually be quite rare. The power, that little calculation we did, that assesses the probability of an experiment to identify the important effects. It's driven by that signal-to-noise ratio, the delta Y we choose, and the standard deviation inherent in the system, and we typically want to see power be 80 to 95%. If it's lower than that, we probably want to add some runs to get it a little bit higher. Now, I did mention, here's a little tip. I did mention that we might have been able to do this in 16 runs because we had that green experiment that was just above the 32 run experiment. And in that case, we would be able to understand the main effects and the two-factor interactions. Okay, but not three-factor interactions or higher, which is generally a perfectly acceptable assumption to take, that three-factor interactions and higher are sufficiently rare. But we might lose power. So in this case, the power would have been 77% had we chosen that 16-run design. Would I run that experiment? Well, I'd have to take a decision. It's a little bit below my 80% rule of thumb. And if I could afford 32 runs, I probably would do it. If I was willing to take the risk of maybe not quite finding everything that gives a 3 percentage point change, maybe the 77% is okay, and I'd have to take a choice, right? So I'd probably run the 16 in most cases, but that's a choice we'd have to make. Okay, so that's a full factorial design. Now the next one we're going to look at is a response surface design. And response surfaces are helpful when we want to truly optimize the system. So if I look at the graph on the left, I'm plotting two different factors along the bottom, X1 and X2. And I'm looking at the response surface, right, this colored surface for my response. Well, the one on the left is a two-factor interaction. A two-factor interaction term can put a twist in the plane but it cannot create a hill or a valley in the response surface. To do that, I'm going to have to get a little more sophisticated with my predictive model. And for nonlinear systems like this one on the right-hand side, I'm going to have to add, say, some quadratic terms or some square terms in order to fit a hill or a valley on the interior of my design space. Oftentimes, if you're optimizing a system, the magic happens on the interior of the design space, and we will want to go beyond just an interaction model so that we can navigate the design space and make good predictions within it. That's where response surface designs come into play. So in this upper right-hand side, this is kind of how a central composite design works. The blue corner points in this cube represent the factorial points where everything is tested at their high and low level. But in addition to that, we are going to include a center point. Points actually do that multiple times on the interior of the design space, right in the center of the design space. We will also put these axial points, ideally outside the face of the cube. If we must walk them back to the face, we can, but you get better statistical properties of the model if we can move those out a little bit. And that'll give us better predictability, especially in the corners of the cube. All right, so here's a case where we want to find the conditions that maximize the conversion in this little reaction system, while also keeping another property called activity within a target range. So here I have three factors, and typically we want to, with an RSM, we want to only work with a handful of factors, those that survive the earlier screening and perhaps the factorial designs, because this is going to require more work, more runs to fit additional terms. So here we have three: time, temperature, and catalyst. And the goal here is we want at least 80% conversion, and we want to maintain an activity between 60 and 66, with 63 being the ideal set of conditions. Okay, so how do we set this up? Okay, so here's our goal: maximize conversion, hit the proper activity, conversion greater than 80%, and target activity of 63. All right, so let's set that one up. And I have this one created right here. Okay, so here we're setting up a central composite design. So over on the left-hand side now in my design choices, I'm not working with a regular two-level factorial design any longer. I'm going all the way down underneath the response surface section and picking probably the most commonly used RSM is a central composite design. And I'm going to choose my factors. In this case, I have three numeric factors: time, temperature, and catalyst. Okay, so we're going to accept all of the defaults, and we'll go ahead and hit next. I have two responses: conversion and activity. I will finish that. Here's my 20 run design. I'll go ahead and get my data. So this one is going to be reaction, and boom, I have data. So now we need to go and analyze both of our responses. I have two this time, so let's start with conversion. So I'll start the analysis. Now things look a little bit different because we're trying to fit a curve using the best predictive model instead of just trying to identify which factors are significant. That was what a factorial does. Now we're trying to actually fit a predictive equation, and it says that a quadratic model is going to be the suggested model. So we're just going to accept that now, and we're going to move forward. So I hit the model tab, I hit this thing called the analysis of variance again, and I have a statistically significant model, and my lack of fit is not significant. Okay, so we're happy with that. Fit statistics, you can see the R-squareds, etc. So that's all still there. Let's take a look at my diagnostic plots. I've got this one data point that's kind of a little bit off the red line on my normal probability plot. So I'm just going to kind of take a look at that. On the upper right, that point does not seem to be outside the red statistical limits on that one, so I'm not terribly concerned. I can look at the predicted versus actual. And yeah, that data point is a little bit further off the line than some of the others. But then I can take a look on the bottom right for how much influence that data point is having. And I'm going to look at the Cook's distance, and that data point is way down here, which says that if I include or exclude that particular data point from my analysis, it doesn't have a material impact on the results. So I'm not going to worry about it very much. We're going to move ahead. And then I can look at the model graphs if I want to. And just for fun, let's make a 3D surface of that. So there's my response surface. I'm looking at factors B, A, and B. But catalyst also plays a role. And if I slide catalyst to its low level, you can see that it's changing the results a little bit. In fact, it's changing the height and shape of that curve quite a bit because of the strong interplay amongst the factors. Well, let's go ahead and do the same for activity. We'll start the analysis. This time, a simple linear model is all that it is what's recommended. So we'll go ahead and accept that. And we'll look at the ANOVA table. And here we have a statistically significant model. I'm going to highlight something, and that's that factor B has a p-value of 0.34. And if you remember, I said that we're looking for p-values less than 0.05. So I might be able to have an actually better model if I get rid of factors that actually don't need to be in the model. So I'm going to jump back to this model tab, and I'm going to double click on B, and I'm going to click the ANOVA. And now I have a model that does not include B. It is statistically significant. The model lack of fit is not significant. That's a good thing. And I didn't highlight my fit statistics before, but in fact, I actually have a little bit better model by getting rid of factor B because I didn't need it. I was just chasing noise with that. So I'm going to do what's called model reduction, and we're going to see in the next example that I'm going to want to do model reduction. So I just highlighted here what's taking place. We can look at the diagnostics, and that all looks good. So the next step here is we're going to want to optimize this situation for the criteria that I have. Now recall we have two different responses, and we want to hit the criteria for both of them. So I will look at numerical optimization. I'm going to touch on conversion. And conversion, we want to what? Maximize that. And we said that we want to go at least 80%. And if we could get to 100, that would be ideal. So that's my criteria for conversion. I can look at activity, and that we said we want to target a certain value. We like 63 is the ideal, but we want to be at least 60 and no higher than 66, right? So this little ramp shows you the criteria for that, right? We don't want any results below 60 or above 66, but we want to get as close to 63 as we can. All right, then we hit solutions, and it looks for the ideal balance between those two objectives. And we have the time, the temperature, and the catalyst level that leads to the best balance between those two goals. And I have a conversion of 91% and an activity of 63%, okay? We can also look at that using graphical analysis. And if I do that, and let me go to the AC one, because I remember I took B out of it. So what this is saying now, my number one solution is where this flag is planted in the middle of this great big yellow region. But this yellow region lets me know how far I can change my factor settings before I get into trouble. If I go to the left along here, eventually I'll come to the point where I go below 60 in activity, okay? If I go up or down, then I'm going to start getting in trouble with the conversion of 80% that I want to have, etc. So this gives me the region of operability where I would meet all of my criteria. Okay, so we've done an RSM to optimize the system. We found the ideal conditions, and we can get an idea of how much flexibility I have around that ideal ideal situation. So an RSM is useful when curvature or nonlinearity is anticipated within the design space. The model terms include quadratic or higher order terms in addition to the main effects and interaction terms. This will require more runs, right? So we want to work with as few factors as we can, otherwise these experiments become very large. And we can use numerical and graphical optimization tools to find the optimal conditions to satisfy multiple criteria. All right, so that's an RSM. So if that's the type of work you do, you may be interested in a little bit more training on that, and we would recommend that you go for a modern DOE for process optimization training. And these are distance learning courses right now, thanks to COVID. But you can sign up for our public courses as an individual, or if you have 6 or more people, we can bring it to your company directly. And if you're interested in working more with response surfaces and factorial designs, you can learn more at staties.com or contact workshops@staties.com for more information on that. Mixture designs are a little bit special. They are RSM designs, but we have a particular problem we have to address. Now, in a mixture or formulation, the factors are ingredients of the mixture or formulation, and the response is actually a function of the proportions, not the absolute amounts, okay? And why this is important, if we think about it, with a factorial design, okay, what we're doing is we're studying each factor in combination with the other one at the high and low level. So let's look what happens if we try to make lemonade, a formulation, with that principle. Well, on the bottom left, we have a 1-to-1 ratio, right? 1 lemon to 1 glass of sugar water. Then on the right-hand side, we have 2 lemons to 1 glass. Then in the upper left, we have 1 lemon to 2 glasses, and in the upper right, we have 2 to 2. Now, the problem with that is I really have the same experiment being run twice, right? The lower left and the upper right are the same formulation. I just have more lemonade. So that messes up the mathematics involved to do the calculations in a factorial design. So, and let's extend that a little bit. If we have 3 factors, instead of being able to independently go to each corner of the cube, because I'm working to a total mixture that sums to 100%, my design space is not a cube any longer, it's this flat triangle, okay? So we have to make an adjustment to our logic if we are going to do mixture designs versus factorial or standard RSMs. So let's get into a mixture design, but in fact, I'm gonna go to a little bit more complicated design where I'm going to bring in a process factor, a mixture plus an amount. Well, a mixture and amount study, some examples might be fertilizer, where the impact not only is dependent upon the formulation of the fertilizer, but how much you use, right? Both can impact the yield of a crop, for example. Medicine, if I'm looking at an Excedrin to cure a headache, right? Well, an Excedrin is a combination of 3 different ingredients, caffeine, aspirin, and Tylenol. So the effectiveness of that medicine not only depends on the combination of the ingredients, but also on the dosage. I can take 1 tablet or 2 tablets, right? So the impact of a medicine, it's a mixture plus an amount type of problem. This little prism at the top kind of depicts the design. I have 3 components in my Tylenol and my Excedrin, for example, and then the amount or the dosage, I could have 1 tablet or 2 tablets. That's along the bottom edge. So here we're going to quickly do a little example for an ibuprofen coating. What we're trying to do here is have a timed released tablet for ibuprofen, and we're going to put a coating on it, on the tablet, on the ibuprofen tablet, which will involve 3 different ingredients to keep it simple: EA, MMA, and TEC. It's a latex emulsion, and the total of those 3 ingredients will be 31% of the total formulation. The other 69%, probably mainly water, will be held constant throughout the experiment. So we're only changing the 31% portion of the total. I have two different, I have the process factor, the coating amount. In my lab coater, I can go from 15 to 25 milliliters injected into the laboratory coating unit. Okay, so that's the amount that we'll be looking at. And my response is going to be the cumulative amount of drug dissolved in 1 hour versus 12 hours, okay, because I want a time release tablet. So let's see how to set this up. All right, so there's what we're trying to do. We want to have 20% dissolved in 1 hour and 90% in 12 hours. And let's see how we set this up. So let me go back to the example case here. So now my design choice, if I look at the left-hand side of the screen, I'm going to go all the way down to the bottom, custom designs, optimal combined design. So that's what we're using here. I have one mixture that I'm looking at, and I have 3 ingredients in that mixture, and I have 1 numeric factor, the amount. So 3 and 1. I will hit next here. But the total amount of my formulation is 31%, because that's the part that I'm changing. So I'm going to hold that at 31, and then I have 3 different ingredients that I'm letting go from 7 to 20, 7 to 20, and 4 to 14 for the third one, right? So that's the formulation I'm interested in evaluating. I will change the 1 process factor, the coating amount, from 15 to 25 mLs injected in my laboratory coater. I will hit next. It will create this standard design that we won't delve into the details. We will just accept its default, which will look at a quadratic mixture and a quadratic for the process factor. I have 2 different responses, the amount dissolved in 1 hour and 12 hours, and we'll finish this design. It'll take a moment. All right, there it is. So now we go get data. And this one's called Ibuprofen. And like before, once we have data, we will analyze each of our responses. Okay, so from here, it's pretty much the same as an RSM, except that I have to make a decision on not only the mixture, but also on the process, because I have to size the model or establish the correct model for each. So this is going to be quadratic bilinear is the suggested model. Okay, we'll just take the software default and move forward with that. So I'll hit the model. Now remember how in the last time I did something called model reduction, and I went to that factor B and I just manually removed it? Well, with these more sophisticated models, especially these combined designs, we typically want to go ahead and do model reduction, and there's an automated way to do that. So I'm going to hit auto select, and to make a long story short, I'm going to run something called AICC backward is the approach that I will take to do model reduction. So I'm going to hit start, and it'll take out certain terms, and I accept its suggestion, and now I have a simpler model. I will hit ANOVA. I will get this little warning that the model is not hierarchical, and the answer to that question is always yes. So it's going to bring back a couple of those terms that I got rid of. And there it is. So now I have a significant model. My lack of fit is not significant. That's good. I have very good fit statistics. Okay, so I'm happy with that. I want to take a quick look at the diagnostics. And there's nothing funny there, so I'm happy with that. Now I'm going to do the same for the 12-hour one. Start the analysis. This one's quadratic bilinear, but it's going to also look at this other thing called the KCV model. It's a particular subset of terms that comprise something called the KCV model, and in this case, it thinks it can do a better job fitting the KCV, so we'll accept that as the default. So you can see the mixture order and the process order are all KCV. I will do the model reduction again using AICC backward as my #1 choice. So I'll accept that. A little bit simpler of a model now. I'll hit the ANOVA, and there it is. So now I have good fit statistics and a good fitting model. Okay, I'll check my diagnostics again. And that all looks good. I don't see anything to be concerned about there. So now we can optimize the system and go see if we can find a formulation and coating amount that will satisfy both of my conditions. Well, how do I do that? Well, I will go to numeric optimization. I will click on dissolve in 1 hour, and I have a goal for that one. I want to target 20% on that one. And I will accept anything from 10 to 30, right? Those are the, it's got 20 is ideal, but it's got to be at least 10, and I don't want more than 30 released in 1 hour. And for 12 hours, I'm going to set a target for that one. And I want that one to be 90%, and I don't want it less than 80. Oops, I made a mistake here. Let's try this again. Oh no, what happened? Yikes. Okay, made a little mistake. So let's go with dissolve in 1 hour. That one needs to be 90. It's got to be between 90 and 100. Excuse me, 80 and 100. Got myself bollocksed up here. There we go. That's my criteria. For 12 hours, I want it to be between 80 and 100, with 90 being ideal. So then I will hit the solutions now that I have my two criteria. And there it is, right? So this is the formulation along the top. I want EA at 13.9, etc. I want the coating amount to be around 18. And then I will hit my requirements, not precisely where I want it, but certainly within my acceptable range at both ends of the timed release. Okay. We can also look at the graphical tool as well, which I think is helpful. I like to look at this one. So this is telling me, this is a complex little graph, but again, this little orange region is telling me where I satisfy all the conditions that I set for myself. I kind of had the formulation along the edge and the coating amount along the left-hand side. This TEC, the third ingredient, is all the way at the lowest point. That was a set point for that one. And if I increase that, you can see that I destroy the region of success, right? So we want that all the way to its minimum amount, okay? All right, so let's wrap things up here a little bit. So that's a mixture amount. So we're working with formulation plus a process factor, bringing the whole story together. Mixtures have a built-in constraint. The formulation needs to sum to a total. So we can't use standard RSM or factorial designs with a formulation. So we need to make some adjustments. Mixture designs are used for optimization like any other RSM design, but because of the constraint total, we have to use special approaches. We can create custom optimal designs that combine the mixture components and a process factor, in this case, the amount of coating that we used. So if the type of DOEs you need to do are more in the world of formulation or formulation combined with process factors, all right, you're baking bread, you not only want to know about the temperature, time and temperature in the oven, but you want to know about the formulation of the bread itself, put those all together in one package. Well, that's a mixture and a process design. So that's a combined design. And if that's the space you operate in, you might be interested in training for mixture designs for optimal formulations. And once again, we have courses for individuals, or if you have 6 or more people, we can bring a custom class to your company. So again, staties.com to learn more, or contact workshops at Staties if you have an interest in that. So in summary, a DOE is a planned multi-factor approach to efficiently and effectively determine cause and effects relationships. The DOEs provide statistical power to add credibility to our conclusions. Design Expert software is specialized for DOE, and it provides a wide variety of design types and modeling tools to address virtually all experimental needs. There are books available if you're interested to kind of walk through a little bit more of the details of this. These are very practical books. These are not deeply, rooted in statistical detail. They're very practical guides for experimenters. So there's DOE Simplified, RSM, and then formulations. So those are available. We have success stories that might be of interest to you, and you can find those in staties.com under publications. We also have material on YouTube, Statistics Made Easy. Lots of white papers and other publications at staties.com. Within the software, on each screen, you can hit the light bulb and that will give you context-sensitive help. So if you don't know what you're looking at or how to use it, go ahead and click on the little light bulb and it'll bring you some guidance. You can email questions that you may have to stathelp@staties.com. That's often excellent response with those, so feel free to do that. And that wraps us up right on time. So thank you very much for attending. I think Sherry is addressing a few of the questions, so we'll stay on the call for just a couple more minutes. But I encourage you to continue the journey. Let us know how we can help, and please make the most of every experiment. And thank you for attending.